Hello, I'm just outside playing with my new toy. This is a u-blox or micro-blox C94M8P application board. Well, it's one of them. This is the one that's functioning as the rover because these work in pairs. So one has to be the base station, which is over there, and that stays stationary while the rover obviously roves around. And this is an RTK capable GPS, so it's giving me very, very fine precision locations. Unfortunately, I can't put my camera, my video camera, in this region here because it upsets it. Oh, damn it. It looks like I've already upset it, or something's upset it. See this little LED here on the right, the green one, when that goes solid like it just did, it means we have a valid RTK fix and we should get the good results that we expect. But I have to just hold my camera a reasonable distance away and try and zoom in like this. So the antenna on the left, on top of the ground plane here, this is the antenna for the module that we just looked at. And over here I have an M8N, a little bit more of a regular GPS, and this is showing us exactly the same thing. Well, it's running, there's a Maple Mini here that's running exactly the same program as this other Maple Mini over there, which is connected to the RTK GPS. But if we look at the difference in the results that they're giving us, and unfortunately, like I said, I can't put the camera too close, but hopefully we can keep that in focus. Okay, so it says at the top there 14, I think, satellites, and the next row down says horizontal accuracy of 14 millimeters. Yes, you heard that right, 14 millimeters accuracy. And the large number in the bottom is the distance in centimeters from the location it was at when I pressed reset button on the microcontroller. So the correct answer is 0 because I have not moved the modules at all. So 1.4 centimeters, 2.4 centimeters there is pretty good, I think you'll agree. In contrast, the M8N is telling us that it is 1.3 or 1.2 meters away from where it started, even though it has more satellites for some reason. What does that say there? 16 satellites, I think. But it's only giving us a horizontal accuracy of 1.7 meters at the moment. So that is the difference in performance, and I uploaded a video the other day where I moved the module along here, and you can see it's actually following very, very closely with the distances on the tape measure or the ruler, but it's quite hard to measure that, so that's why I'm just sort of standing back and zooming in here to show you what's going on. But I've placed it on a board here, and I have some nails. I've got 3 nails here so that I can put it back in exactly the same position if I take it away. So let's just go for a little walk, and we'll go over there. And I found a spot over there which is exactly 10 meters away from the starting point. I'll see if I can get it to do it, because with the accuracy, oh damn it, I touched something in this. That one's frozen, and that one's still going. Alright, damn it. There's a little bit of amateur wiring going on here. Something in this microcontroller, when I touch it, it likes to reset. So let me do that again. Okay, that's better. So as you can see as I walk, when I stop, it just stops, pretty much. So I can make it say, if I'm careful enough, I can make it say whatever number I want just by, it's the number of the beast. See, I can put it right on there. It's a little bit hard to hold this with one hand while you're filming, but if you hold it carefully, you can make it say whatever number you want, just about. But anyway, this is my post where I found a 10-meter distance spot. Let me just put that down there. See, there we go, look at that. 989, if I just rotate it around a little bit that way, should be able to get this to say 10 meters exactly. Alright, that'll do. A little bit more. There we go. 10 meters. And notice how it just sits there on that number. So this point here, well, it's where the antenna is the point. Is exactly 10 meters from the point where the antenna was over there, and it just sits there. on that number. Isn't that great? And this one is saying 9.3 meters, which is not too bad. I mean, keep in mind the difference in price between these two modules is quite extreme. So given that you're only paying about $20 for one of these, that's pretty good performance there still on the right. But look at that, it's just sitting there, wow. Alright, so if I carry this back to where I started, hopefully without bumping that wire again, kind of have to hold it from this corner. I should be able to get it to go right back to 0, or 1.1 or whatever it was, just by putting it up against those nails that I had. Let's see. So it's like that and up against that nail. And there we go, back to 0-ish. And this one thinks it's 1.6 meters away, 1.5 meters. Oh, it's slowly coming back, isn't it? But anyway, it's about 1.5 meters off the true value. So hopefully that should give you a pretty good picture of the difference in performance between these two modules under the same conditions. Exact same program running on the microcontrollers, and exact same time of day and satellites and everything. Perfect side-by-side comparison.
Now I realised that I probably just glossed over a few terms and concepts in that intro there that some viewers may not be familiar with. I kind of think that most people watching this video would be familiar with what RTK is all about, but just in case I will go over some of the background about how it works and how GPS in general works and why the RTK method can give us so much better precision. So I'm just going to read this from navipedia.net, which is a pretty good site for all this kind of information. Real-time kinematics is a differential GNSS technique that provides high performance positioning in the vicinity of a base station. So this is a requirement. And just to go back one step further about how GPS in general works, we have a bunch of satellites up in space, and each satellite broadcasts a signal with its location, status and precise time information. And the speed that that signal goes down to Earth and is received at the receiver is known. That's a constant 300 million meters per second. No, what? 300 million... Is that right? Kilometers per hour? I thought it was 300 million meters per second. Anyway, it's fast, whatever it is. Then the GPS receiver receives that signal, notes the time of arrival, and uses those times of arrival to calculate its distance from each of these satellites. And when it knows how far it is from each of them, it can use that information to triangulate its position on the planet. And this signal that it's sending here is... This is where my understanding may slip a little bit, but it's sending a pseudo-random code. So this is just some pseudo-random code that I generated from a website on the net that lets you do this, and it's just a sequence of, in this case, numbers and letters that is not perfectly random. It looks a bit random, but each of the satellites will be transmitting the same thing, and it goes on. It's very, very long. It repeats after about 1 week, I think. And the way that it works is that the receiver will look in this random string, pseudo-random string, and it will try and match up the signals that it's receiving from each satellite. So we can see at the beginning here, satellite 1 is sending us this KHUOAV part, and that repeats here, or it shows up in the signal from satellite 2 over here a little bit later. So KHUOAV is this bit here. So from this we know that satellite 1 is a little bit closer than satellite 2, and then satellite 3 has this P0LLFBU, which shows up here from satellite 2 and there from satellite 1. So satellite 3 is actually even closer than satellite 1. I think that's how that would work. So it'd be, this is the closest, then that one, and then that one. And we know from the difference in the time of arrival of these signals, we can get an idea of how far away these satellites are relatively from our position. So this signal here is the content of the signal that's being sent, and as you may know, the frequency that this is sent on is about 1.5 gigahertz That's how the receiver will be picking this up at that frequency. This information is not coming in at 1.5 gigahertz. It's actually about 1 megabit per second, so it's quite a bit slower than the frequency that it's being carried by. So RTK consists of a base station, one or several rover users, and a communication channel with which the base broadcasts information to the users at real time. Now, why would we want to have a base station, and why would we want to have it broadcasting information to the users, and what would the information be? To think about why we might want to have this, consider that when the satellites send this signal, it has to come a long way from where they are down to the receiver on Earth, and it's about 20,000 kilometers, I guess, from what this is telling us. So there's a whole bunch of errors that can creep in along the way. The clock and the satellite, well, I'll just let you read them there. Ionospheric delay, tropospheric delay are quite important as well. This is just the upper levels of the atmosphere. The signal gets delayed as it passes through. Then the receiver clock is offset. So there's a whole bunch of things there. But consider that if we had another receiver here next to this one, just pretend that I wasn't lazy and I drew a picture here of another receiver right next to that one. The errors that the second receiver would accumulate or receive would be almost exactly the same as the one that was right next to it, as long as it was in the same location on Earth, because it would be coming from the same satellites, and the signal would be traveling through the same part of the atmosphere. So these two receivers right close by each other, if you looked at the error in one of them, it would be the same as the error that the second one received. But let's suppose that we know that our second receiver is not moving because it's a base station that we fixed in place. When the base station receives some signals that say that it moved, it knows that that's an error because it's not moving. So it can transmit to the rover, this pink one, it can tell the rover what errors it received. So the rover will know what all these errors are, at least the sum of these errors. And the rover can use that information to correct its own position. So that's what it means when it says here, in the neighborhood of a clean sky location. So as long as both of these two receivers are in the same area, the main errors in signal processing are constant, so they can cancel out when differential processing is used. That's what it means, differential GNSS technique there. So this includes error in the clocks and the atmospheric delays that we just looked at. So that's part of what's going on, but the really neat stuff is what comes next when we start talking about the carrier wave. So the carrier wave is the 1.5 gigahertz radio signal that is being used to carry that pseudocode content. And there's a little diagram on Wikipedia that sort of illustrates this a little bit. So the carrier wave is this 1.5 gigahertz wave, so it's going up and down very, very quickly, obviously. And then the information that's carried on that is a lot slower. So there's this course acquisition code, and then there's actually a couple of other things that are being carried on this as well. But anyway, this is the wave that we are trying to look at now. And here's another diagram which visualizes this wave between the satellite and the receiver. So the wave, you can sort of picture it as sort of going down and then up again. And that's one cycle or one wavelength. And it's going down and up 1.5 billion times per second, is it? 1.5 gigahertz is 1 billion? 1.5 billion, I think. Anyway, if it goes down and up again and it moves at the speed of light, that means that one wavelength will be about 19 centimeters. So the objective of this RTK algorithm is to figure out how many of these waves are between the satellite and the receiver. And that's quite a tricky thing to do, but as it happens, the ambiguity, when it says ambiguity here, what it means is that we have a wave that goes up and then down, and then the next wave also goes up and then down. So how do we know which is which? Or how can we tell how many of them there are in this distance? So another way I like to think of this is, suppose that you have a friend out on a boat in a lake, and your friend is jumping up and down on the boat making waves, and you're standing at the shore watching the waves come in. Each wave comes in, looks just the same, so it doesn't really tell you anything about how many waves there are between you and your friend. But somehow this ambiguity can be fixed for dual frequency differential measurements for two close receivers. That is the important point there. So what needs to happen for this to work is that the base station will broadcast its location together with the code, the content, the pseudocode stuff, and the carrier measurements that it sees for all in-view satellites. And with that information, the rover equipment is able to somehow, with black magic and voodoo, it's able to fix the phase ambiguities and determine its location relative to the base with high precision. So you still need to give your base station an accurate location if you want to get a global position that's accurate, but sometimes just a position relative to the base may be good enough. And then by adding up the location of the base, you can put the rover in a global coordinate framework. And as it says here, this technique can be used for distances of up to 10 to 20 kilometers. That means between the base station and the rover, and it can yield accuracies of a few centimeters in the rover position. Very nice. And it's used extensively in surveying applications. So there are some limitations. As we just saw, there's a limited range with respect to the base station. It needs a communication channel. In this case, we're using radio transmission, UHF radios, because it needs, all that information needs to be transmitted in real time, and there's quite a lot of information to transmit. And it also takes some time to converge to figure out these quite complicated calculations, and the time will depend on the distance between the base and the rover. Ranges from a few seconds to a few minutes. What I've seen so far is it's about a few minutes, even though I'm right next to the base station. In order to avoid reinitializing the processing, the rover has to track the signals continuously, so that means it's not suitable for urban applications. So if you're going in between buildings and stuff where you lose the signal just for a moment, that's going to ruin the algorithm solving, because it's going to have to start again, basically. I think that's what that means. But if you're out in the middle of nowhere like me, then it should be fine. So the modules that I was using in the demonstration at the beginning of this video are these Neo-M8P modules. And as you may have guessed from the explanation that we just went through and the complexity of what they're doing, these are not your average hobby grade cheap GPS modules. And you can see over here, standard is grayed out and professional is blacked in. And I guess the elephant in the room is, how much do you need to pay to get this kind of centimeter accuracy? So scroll down a little bit, you'll see some prices here. These are prices for just this module here, so that's like $100, and this one's only with rover functionality. So to get this to work, you would need to make your own PCB and solder on there somehow. And then for one that can be a base station, it's $125. So definitely quite a bit more than your average M8N module, which you can pick up for about $20. But obviously the functionality and the precision is so much more. So I started looking around at these, and I initially thought they were in the thousands of dollars range, so I was quite pleased to see that they were not. And I was also quite pleased to see, if we scroll down here, u-blox also makes something called a RTK application board package, and if we just have a look at that, that's this one over here. So this has two of these modules set up with a UHF radio and all the antenna connectors and supporting voltage regulation, RS-232 plugs, USB plugs, whatever that stuff is there, some LEDs, capacitance, pin headers, battery terminal connectors, everything you need to get started. Plus, it's very, very simple, just about 5 minutes of setup, to be honest. If I had have just gone straight through it quickly without having to read all the documentation, it's just 5 minutes of setup. And these are $400 basically for one of these. So again, it's not cheap, but it's not in the thousands of dollars range like I had originally been worrying that it was. Still, to be honest, a little bit more than I wanted to spend, so I rather cheekily asked if I could get a discount on one of these from u-blox, and they quite generously gave me one of these packages to test and review for YouTube. So you can thank Sven at u-blox for giving me this to test. To be honest though, I am partially sponsoring this myself because I'm a little too embarrassed to say exactly what happened, but suffice to say I ended up buying a second application board package myself because one of the modules that I got in the original package got damaged somehow. Yeah. So yeah, thank me as well for this one. But if it was not for u-blox having sent me the first package, then this video would not have been made. So most of the thanks goes to u-blox here. So this is how the application board package will arrive. You get a couple of fairly large UHF antennas. This is the 900 megahertz version that I have here. The two modules themselves, these are the same, and I have the 4 variant there. And then we get a couple of USB to micro USB cables and some nice big GPS antennas, which are apparently quite magnetic. Wait a minute, is this not... It's not aluminium, I don't think. It's quite heavy and quite stiff. I thought that was aluminium, but that is not aluminium. Wow. Look at the size of this. That's got to be 4, maybe even 5 centimeters across. 4.5 or so centimeters across. It's a big one. And of course you get 2 each of those, so there's another 1 each of those, and that's all we get in the kit, I think. Yeah. Let's take a closer look at the application board itself, and we can see on the right hand side there in the silver can that is the UHF radio module, and in the left on this underneath this plastic cover thingy is the GPS module itself. I have to confess I don't really know why they went to so much effort to shield it like that. I don't think it's airtight or anything, it just sort of seems to be a plastic shield. So I'm guessing maybe it's just to stop you from putting your fat fingers on here and touching it, and maybe, I don't know, electrostatic discharge from touching it or something like that might be very sensitive, that kind of thing, perhaps. I don't know. Anybody know? It says Hammond 1551N on there, just in case that means anything. But it's not just the GPS module under there, there's a bunch of other things as well. Looks like a few other little bits and pieces. It's a bit hard to show you here because the camera is going to focus on the upper surface of this plastic instead of the board underneath like I'm trying to show you, but you should be able to see that there's a bunch of little bits and pieces in there as well. Anyway, so we have the UHF antenna connector there, GPS antenna connected there. We have some interfaces here. This brings out most of the pins from the GPS module as far as I can tell, and I'm hoping to use this to connect UART connections on here for Arduino and things like that. Over here this brings out some of the pins from the radio module. Probably won't be using that too much. Up here we have an RS232 D plug, and top right corner is battery connection, so that's up to 20 volts. And in the top left corner we have 2 LEDs. One is to tell you when you have a regular fix, like the same as you would get from a peasant's GPS, and the RTK LED will tell you, show you the status of your RTK fix or floating or whatever it happens to be at the time. And then we have a USB, micro USB connector over there as well. So this might be a good time to show you something that I discovered in the documentation. This is in the app board user guide, and it's just sort of showing you very broadly how these things are all connected. So power is pretty obvious, but it does show us at least that internally everything's running at 3.3 volts, so the radio module and the GPS itself both are running at 3.3. The USB will go directly into the GPS module. It's probably the quickest and easiest way to set things up, but you can do it in the same way as I've done in the past by sending the UART, sending messages through the UART. But you have to keep in mind that this UART here is shared. It's going to the RS232 plug, to the the black plug that I showed you, and it's also going into the radio module, because when it's sending those RTCM3 messages, it's going to be sending it through the radio module, obviously. So one thing that this does make possible, of course, is that we have a route to get from outside into the UHF radio module directly without having to bother with this. So that means we can change some settings in the UHF radio module. And I may actually try that, because I was quite interested to see in some of the other documentation somewhere they actually link to the ArduPilot mission planner or something or other on the ArduPilot page that they link to, because the radio that they're using is apparently very similar to the kind of thing that you use for your ArduPilot telemetry. So what we have in here is very, very similar to what we have in here. And they go into quite a bit of detail explaining how you can use something like PuTTY on Windows, or a normal telnet sort of an AT command terminal to talk to this radio module and change things like the lower frequency and the upper frequency and the number of steps, no, what is it called? Hops, number of hopping frequencies. But I suspect you may actually be able to use ArduPilot Mission Planner to do all that setting up in a bit of an easier way, so I might experiment with that. That would be in another video though, I think. Anyway, so on the back of this we have nothing much, but we do have some very nice sort of hard rubbery plasticky feet to keep it all off the ground. The UHF antennas are 17 centimeters long overall, which is quite a bit longer than the cheapy antennas that you get with stuff like this Hobby King telemetry module that I got a while ago. And I think what's going on is something similar to this one here that I made a while ago. I was reading on the net about how to do this, and a simple way to make it, I think it's called a sleeve monopole, or is it a sleeve dipole? I don't know, I always get the terminology wrong with antennas. I think it's one of those. And you just take a length of coaxial cable and you fold back the shielding. So from this point you obviously you cut it there, and then up to about here you fold the shielding back around the outside. So from this point down here the shielding is sort of doubled up on the outside of the plastic tubing, and that will give you two lengths of, in this case it's approximately 8 centimeters there and then 8 centimeters there, and that sort of fits with pretty much what you have in that same sort of a length there. So I'm guessing that inside this is something very similar to what I have here, but perhaps a little bit better made. And these come with SMA. That is SMA, isn't it? I think it is. Anyway, it's the same as this. So if you do have some of these Hobby King modules, you can put that on there, and you may get better range than you get with the cheapy one that came with these modules. So I might try that sometime in the future and see if it makes any difference. Here's the GPS antenna and the ground plane. The ground plane is 10 centimeter diameter. The GPS antenna looks like it is indeed about 4 centimeters square. It's pretty big. Makes this other GPS module that I have here, this is a Neo-M8P that I've had for a while, and it has a more typical sized antenna, but the actual module itself is in there as well. But even so, this antenna just dwarfs it when you put them side by side. I'd kind of like to see what the actual patch itself looks like, but there's just no clear, easy way to get in there, and I don't want to break it before I've even used it. And like I said, there's a big magnet on there. It's quite strong. So the cable looks like about 2 meters. I'll measure that and put it on the screen here, hopefully, if I remember. And again, we have SMA. So the weight of these things is starting to get a bit up there. So if you're going to be putting this stuff on any kind of a flying vehicle, you might be concerned about that. So let me just weigh all of this stuff. So the module on its own is 54 grams, 28. Told you that's pretty heavy. 95, yeah. Keep in mind though that you don't strictly need to use this exact ground plane and this exact antenna, so you might be able to get away with swapping this stuff out. See, this technically is kind of optional, but typically you're probably going to be putting this on a pretty big drone. That wouldn't matter, wouldn't worry about too much of that weight being added. But this weight here is non-optional, obviously. Oh, guess we should probably put that on too. Ooh. So for the mathematically challenged of you, that's the total weight of all of those. Okay, so what I'm going to do now is go through the quick setup guide, which explains how to get these two modules up and running, and you can find that on the main page if you scroll down to Quick Start. It is this application board setup PDF, and I found this document fairly early on when I was investigating all this stuff, and I have to admit it is partially, if not entirely, responsible for me wanting to get a couple of these modules for myself and try them out, because it just makes everything look so easy. By the way, this photo looks a little bit photoshopped, doesn't it? I don't know if the bikes really fit into this picture too well, And I certainly wouldn't be grinning like that if I just cycled up the side of one of these mountains. Probably be ready to collapse in a sweaty pile on the ground. Maybe that's just me. Anyway, so the connections there, we saw that. Setting up, obviously you need to connect the antennas, two antennas, and then it says connect the USB port on the board to a PC for power and configuration. That is obviously the easiest way to do it, and that's how I did it at first. But to just show you exactly what I'm doing right now, I've moved to a little bit more complicated setup because I wanted to have my base station semi-permanently outside while I was sitting inside making all the adjustments and configurations, and that just makes it easier than going outside with my laptop to connect to it every time I want to change something, and it also means I can record stuff for YouTube a lot easier. So what I've done here is I'm using I think it's about 8 or 10 meters long piece of telephone cable, and this just lets me get a lot more distance on it than the typical USB cable. To power that, I'm using a DC plug into the wall kind of adapter that gives me 12 volts, and that plugs into this plug here, so I've got 12 volts and ground on the black and the red, and they come through the other end of the wire and go into the battery terminal. Pay attention to the polarity on this terminal, by the way, because it's it's kind of important. The other two wires here, the white and the blue, are the RX and TX for the UART connection, and there's also ground going here because that needs to be common for both of these. And over here you can see I've used the pins are 9 and 10. So starting from here, this is pin 1, that's actually labelled. It wasn't clear from any labelling or any documentation which way it goes, but I just figured out with my oscilloscope that it goes 1, 2, 3, 4 in kind of like a ladder rather than a circular pattern. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9 RX, blue, 10 TX there. So that's how that's all working. Another very important thing to note, this FTDI adapter is a 3.3 volt one, or actually has a jumper on it here so you can select between 5 volts and 3.3 volts. So I'm pretty sure if you use 5 volts on this you might stuff something up rather permanently, but 3.3 volts is working perfectly well for me at the moment. By the way, if you wanted to get some more info and details on this application board itself, you can come back to the main page and scroll most of the way down. You'll see a load more button, and that will bring in a few more documents, and I don't know why they didn't put this one a little bit further up on the page because it's fairly important, I would have thought. But this is the application board user guide, which is this on here, and this will explain all the configuration in quite a bit more detail than the quick start guide does, and it will also give you some more specs, including the one that I was just mentioning here, the J8 connector, which is the pin header, and it also tells you how to connect to the UHF radios to make configurations for those as well. So like if you wanted to change the number of hopping channels, hopping frequencies and so on. So anyway, the J8 connector is this. Where is it? There it is, J8 connector, and there we go. So those 20 pins there are as follows, and the number 9 and 10 are the ones I was just using with RX and TX like that. So once you have it connected to your computer, you should see in the device manager under ports some kind of a COM port that you can use to communicate with the GPS module, and in my case it's just showing up as a generic USB serial port because I'm using that FTDI USB to serial adapter. But if you use a USB cable to plug into the USB port on the GPS module, you should see something with a proper name on here. I think it says u-blox GNSS receiver or something like that. But in any case, there should be some sort of a COM port here, in my case COM14, that we can use to connect with. Anyway, getting back to the quick start guide, we've made the USB connection. Well, it's not USB. If you use USB, obviously it's a whole lot easier than what I just showed you the way I did it, but it does the same thing functionality wise. So the next thing you'll need to do is download the latest uCenter application, and you can get that from that link there. And I kind of think that most people watching this video probably already have this or know what it is, but basically this is the software that allows you to connect up to the GPS module and make lots of neat settings and configure it. So you'd get that for Windows there. I obviously have that already, so let me just start it up and see what we can see. Now, I was using this just before, so it's automatically connected to the last COM port that I was connected to, but if you want to change it, you can do that here in this little toolbar thing. So I'm on COM 14, and the baud rate will most likely, I think it was 9600 when it first arrived. I've been playing around with it a little bit. I've tried to set everything back to how it was when it arrived, and I think it was 9600, but I'm not sure. But if it's another baud rate, it might be that one perhaps, you can try another baud rate here as well. And if we just take a quick look at the packet console, we'll see that the only messages that are coming out of the GPS are NMEA sentences. And again, I've had to set this back to what I think the defaults were when I got it, but the default state of things when the module arrives should be something pretty much like this. As the next step, it is recommended to update the firmware. I found that this was not necessary. It mentions what the latest one is here, HPG 1.40. Information on the latest firmware is published on the u-blox website. To update the firmware, follow the steps described in the U-Center User Guide, Chapter 8.1, Firmware Update. So that user guide you can find on the page where you get the U-Center. It's this document there, so look for section 8.1. It will explain how to do it. And you will need a firmware file, which you can find again on this main page. If you go back here and scroll down, there'll be firmware files somewhere or other, firmware update. There's a few of them listed here, but notice that these ones are legacy, so these are the older ones. The one at the top of this list here is HPG 1.4. So that is the latest one, and I'll show you just in a second how to check which one is running on your GPS module. So pretty much all of the configuration takes place in the messages view, and when you open this up, move this bar across a little bit and you'll see a tree expansion contraction thing here. It would be nice if you didn't have to do that, but anyway. Under the UBX tree, branch, whatever, you'll see some subsections. Let me just maximize this window. So there's some subsections to this UBX part, and this config here is where a lot of it takes place, and you can expand that and see that there's a lot of subsections under there as well. And also monitor and navigation seem to be the ones that I'm using most frequently. I don't think I've used any of the other ones actually, but if we take a look in monitor, we'll see one right down the bottom here, version, and that will tell me that the firmware version that I have on this GPS is the current HPG 1.4. So the firmware is up to date here. I don't need to do anything. So getting back to the quick start guide again, I'm not going to do anything about the firmware. I'm just going to skip this page and go on to configuring the base station. So at this point the two boards are identical. Everything we've done up to here will do for both of them. We haven't actually done anything really though, have we, apart from plug them in. Anyway, we need to select one of them to be the base station, which I have done by putting it outside, I guess. And there are 3 steps that we need to do. Set the position. So the base station needs to know where it is to pretty good accuracy, and you can do that by doing something that's called a survey in, which means you just leave it running for a while and get it to take an average of all the points that it sees while it's sitting still, obviously, and that will give it a better average over a long term. So I think probably 24 hours would be a good time to do this for if you wanted to have a serious permanent installation, but as we'll see on the next page, even about 10 minutes is often good enough. The other way you can tell it where it is to actually just give it some coordinates. So if you've already done a survey in, or if you have some coordinates that you know from a actual surveyor's, land plans or whatever like that, you can just tell it those coordinates. Next step is to set up the port for the radio link. So we need to tell it that it needs to send UART messages out through the UHF radio. And the third step is to say which messages. So we want the real-time correction messages, and we need to tell it which of those RTCM messages to send. So step 1 is to set the base station coordinates. So we use this config time mode 3 message, and we can either tell it to begin a self-survey or survey in, or we can provide a fixed position estimate. So there's 2 sections to this page here, and you'll make a selection here as to which one you want to do. So let's have a look at that. So what was it? Config T mode 3, this one down here, and it's disabled at the moment, so it's just running as a normal GPS, and we can see over here it's just a normal 3D fix, just a plain old GPS functionality at the moment. And if we select fixed mode, we'll enable these inputs here. You can also input in lat long alt. The default is this meters coordinates, but you can make it alt. Lat long out if you want to. But what we're going to try here is a survey in, So we would select in here a minimum observation time in seconds and a required position accuracy. So this is saying you want an average accuracy, statistically speaking, of better than, for example, 2 meters or something like that. And even if you get to that accuracy, you might want to still keep it running longer to get a better accuracy than that. So you could put an observation time in here of, say, 3 hours or 4 hours or whatever, and it will finish, the survey will finish when both of those conditions are met. So not just one of them, it's going to keep going until they're both done. Alright, and let's just go back here because what does it say? 5 minutes, for example, use 5 minutes and 2 meters. With a good antenna and a friendly multipath environment, you can reach 1 meter with a 10 to 15 minute observation time. I tried this and it took about 17 minutes, but this was before I put it on the car. I had it just sort of outside without such a good ground plane. So that's not too bad. 1 meter, and it's about accurate, I suppose. Next page here explains how we can know when the survey in process has finished. Now, obviously, if we set it to do a 24-hour survey, and we would expect it to finish after 24 hours, but if we are relying on the condition, if we're more concerned about this accuracy in meters, we don't really know when it's going to finish. So we can look at the nav survey in message, and this will allow us to monitor the survey process, and we'll have a look at that in a second. The other way we can know when it's done is by looking at the fixed mode, which will change from 3D to time at that point. So let's just take a quick look at the what was it? I've forgotten already. I think it was nav something, wasn't it? So when you change away from one of these pages, it asks you, if you've changed some settings, it asks you if you want to send that to the GPS. I actually don't want to do that just yet because I want to show you what the nav, this one here. So this is under nav. See there? Nav, SVN. And this is not started yet, and it just has a bunch of zeros for the average positions that it's recorded. And this one here at the bottom, mean 3D standard deviation. So this is a standard deviation from all the points that it's collected over the course of the survey in process, and at the moment that's 0, but when we start this running, we'll see this gradually decreasing as it gets a better standard deviation, hopefully, as long as the conditions for reception are good. And when this gets down to the number that we set in the config time mode 3 here, and this value, then the survey in procedure will finish. And just one other thing that I'll point out here, it says, note that you might need to disable NMEA messages to see this mode correctly, that's this here. So before I start the survey in process, I will actually go and disable NMEA messages, which we do by going all the way up top here. And if I expand this, we'll see that some of these are in black as opposed to grey. So the grey ones are not active, the black ones are active. So that's why we're seeing this update here. You can see that refreshing and things are changing and so on. But you can disable all of these in one go by right-clicking on the NMEA parent here and doing disable child messages. And sometimes takes a few seconds to get that through, but now you'll see all of these have gone grey, and the NMEA itself has gone grey as well to signify that there's nothing below this parent that is active. And you'll also notice that all of these updates have stopped, so we're not actually getting any information through. And if I look at the packet console, we will see no activity at all, but that's fine. Actually, I would like to see updates still while I'm doing the survey process. So what I can do is I'll turn on the equivalent u-blox messages that were giving me these satellites and position updates. So under u-blox nav, there's a PVT message, and if we look over on the right, we'll see the contents of this message. This is basically all you need to know about position and movement and everything. So if I right click on this, I can enable that message and give it a moment, and it should turn black, and we'll see now that the details are being updated here again. We're still not seeing the green bars because that is not part of this nav PVT information. If you want to see those green bars, you'll also need to enable the SV information, which I think stands for space vehicle information. So if you right click on that and enable that, you should see it go black, and then the satellite signal strength display will come back. So with these two u-blox messages on, you can get the same information that you were getting before, but you don't need to have any of these NMEA messages running. So if I look at the packet console now, we'll see we're just getting u-blox messages only. So this means that we should be able to run this survey in process without any of this interference from the NMEA messages. Alright, let's go back to kind of bouncing around in these configuration tree, aren't we, here? So it's config time mode 3, and I'll set this to survey in, of course, and I'll give it 10 minutes, which is 600 seconds, and a required position accuracy of 1 meter. I kind of don't think this is going to finish in 10 minutes, but we'll see what happens. So with these two selected here, I can then, you can click on send to send that to the GPS, or if you click away somewhere to one of the other things, it will ask you again if you wanted to send it. So I'll just click send, and well, we don't actually see anything changing here, but if we go to that, what was it, nav? Survey in. So if I look here now, it says in progress, and nothing is, oh, right. When you click on one of these, it will bring one message in. But if you want it to keep coming, you have to enable that message. So now we should see it counting up 43, 44, 45. So it's been running for 46 seconds, and we'll see that the mean standard deviation here should be slowly decreasing. So that's pretty good already, 1.46 meters. So let's see if this can finish in less than 10 minutes, or if it takes longer. I'll cut the video here. Alright, so just coming to the end of this, you can see the deviation, standard deviation is just about to dip below 1 at the bottom. And we're still in 3D, but this is going to go to time here, I think. And the time taken is 690 seconds, which is 11.5 minutes. So, okay, there we go. So it's just gone below 1. Clicked into time there. So we didn't quite manage to do it in 10 minutes, but 11.5 minutes is still pretty good. And just in case it wasn't obvious, now that the fixed mode has become time, this module knows that it's a base station and it's not going to be moving. And even though we are getting updates here, you can see that the signal strengths are being updated and it's doing all the normal GPS receiver functionality. The lat-long altitude here is not changing, but that's normal because it's a base station, so it knows that it's not moving, or it accepts that we've told it that it's not moving, put it that way. Okay, back to the quick setup guide again. Let's go on to the next step, which was to tell this module that it needs to be sending RTCM3 data on the UART1. So this UART1 is the UART port that's connected to the UHF radio, and we can do that pretty simply under the config port branch of the configurations. And we need to make the settings like this. So the target port that we're going to be configuring is UART1, and it's a one-way connection. There's only going to be data coming out of this module and going to the rover. Nothing's going to be coming back from the rover to this module. So for protocol in, we can say none. We're not going to be receiving any information. Protocol out, though, has to be obviously RTCM3, and the baud rate that they're recommending to use is 19,200. This obviously can be faster or slower, but it needs to be the same on both the rover and the base station, obviously. But I would just go with what they've recommended here. Could be possible that something faster than this might not work anyway, so let's just go with that. So to make that setting in here, that was under config port, wasn't it? Ports. And the target port is UART1. Protocol in was none. Protocol out. At the moment we have u-blox and NMEA messages coming out. That's how we are able to see these updates. And just as a reminder, if we look at the packet console, we'll see u-blox messages coming out there. But we don't want u-blox or NMEA. We only want RTCM3, so we're going to select that. And the baud rate should be the recommended 19,200. Now, if you are connected to the application board in the normal way with the USB cable between your computer and the board, At this point you can just click on send and you should be able to continue doing the rest of the process without any problems. But I will have a problem if I do this, because if you recall from earlier, I'm actually connecting to the module by this very UART connection to make this setting. So instead of leaving this protocol in as none, which would lock me out from being able to do anything, I'm actually just going to put that back onto UBX, and that will allow me to still send messages to the GPS from this uCenter application. And I also have another problem here, because I'm going to change the baud rate from 9600 to 19200, and at the moment I'm connected at 9600. So as soon as I do this, all of these updating displays here will stop, but I don't think I should lose connection. Let's try. So send, everything stops. Now let me just come in here and change the baud rate to 192. And if I look at the packet console, we don't see anything here, but this is actually okay. From what I can tell, the RTCM3 messages don't show any display in here, but I think they should still be coming out. All right, so that's what I'm going to leave mine as. So I guess you could do this too, but maybe just a little bit more sensible if you're not actually using this UART connection to put this to none, as was recommended in the quick start guide. Anyway, this is what I'm going to go with, so there, send that. Alright, back to the quick setup guide again. The next thing we need to do is to say which of the RTCM3 messages we want to send. So we're going to look under config message, and we can see here there's a suffix here, 1005, 1077. So we're going to select these 4 types of messages and enable these ones. So that's config message 1005. I'll just do one of them. And obviously they need to be output on UART 1. So config message 1005, let's see if I can find that. Config messages. There's quite a lot of messages in here, but I found these ones are all right at the bottom. So the 1005 is there, and currently that's not being sent on any port, but we want it to go out on UART 1. So I'll check that and do send. And then you'll need to do it for the other ones too, which were 1077, UART 1 on, send. So that was all you have to do for those. And I'm just going to go back to that first one I did, 1005, and see if it still remains on. Okay, it looks like everything is set up okay there. Okay, getting back to the setup guide, that is step 3 finished, and step 3 was actually the last step, so we've finished setting up the rover, the base station now. That wasn't too hard, was it? I think I kind of made it look a little bit more long and drawn out than it actually is, because I'm trying to explain quite a few extraneous details as we go along. But if you were just to sit down and do this by yourself, you'll find that that's probably less than 5 minutes of configuration to do. Well, apart from the survey in process, obviously that's going to take a while, but actual configuration that you need to do is less than 5 minutes work. So the next page goes on to rover setup, and you'll also be pleased to see that there's only one step to that, and it's very, very simple, because as we see here, a rover that receives RTCM messages will automatically go into RTK mode, and no further configurations are needed. So all we need to do is configure the radio link to receive RTCM messages. And if we look at the next page, we'll see something that we've just done for the base station. So we go back to the config port setting, and for UART 1 we need to do basically the reverse of what we did for the base station. So the rover needs to receive RTCM3, so protocol in is going to be that, and it doesn't send anything back to the base station, so protocol out is going to be none, and then the baud rate obviously needs to be set to the same thing as you set for the base station, and that's it. So I'm not going to show you that because I have my base station connected up at the moment, and it's just the same as what we just did anyway, but I'll assume you know how to do that. So rover operation, under normal operation you'll see stuff like this with your regular peasant's GPS. You'll see 3D, DGS and so on, but when the rover is receiving RTCM corrections, you'll see an extra float. It'll either be float or fixed, and the meaning of those is explained here. So it will immediately go into float mode when it starts receiving the corrections, so that just means that the link between the base station and the rover is working correctly. And the fixed mode means that the rover has resolved the carrier ambiguities, and you are now getting the full benefit of all those extra precision calculations. Now that's all very well if you happen to be looking at the U-Center application like this to see that information, but if you're out in the field you'll probably want to look at the LEDs on the board. So they're up on the top left corner there. There are two of them, and the blue LED functions basically the same as on a peasant's GPS. The green one will tell you what's going on with the RTK link to the base station. So it flashes in float mode and it stays on in fixed mode, and it's off when there's no RTK fix at all. So once you've made all those settings, one very important thing that I almost forgot to tell you is that you'll need to save that configuration in the receiver so that when it's turned off and then turned on again next time, it will keep the settings that you made. So I'm just looking at my base station here, and it might look like nothing's working because there's no information in the main panel and there's no signal strength displayed here, but remember that I set my base station to output only RTCM3 messages, and these messages do not carry any of the literal information that these displays need to use. Instead, we're just getting our RTCM3s, so that was 1005, 1077 and so on, and this is the carrier phase data and a bunch of other data as well. Have to admit I don't really know too much about what each of these messages contains, but I'm sure it's all very important. So anyway, to save the configuration in the receiver, you would come into receiver and go into action and save config. So that will make all of the settings that you changed in the messages panel stick, so that next time the module is powered up, well, you won't lose any of these settings that you just made. Okay, well that covers all the setup. This video has gotten way too long already, so I'm just going to stop it here, and I'll continue on obviously with some more videos in the future explaining a little bit of some of the observations that I've noticed while using this, and I'll put it on my farm rover and maybe even my large hexacopter as well and see how it performs on those. But for now, I'll just thank you for watching and see you next time.